So let's now have a look at some questions on physics paper 2. So the first topic we're going to look at is gravitational fields. So the first question says, comets are balls of rock and ice. Figure 12 shows a comet in an elliptical orbit around the sun. The comet is closest to the sun at point P. Table 1 shows the data for the comet at P. Show that the gravitational force of the sun on the comet at P is approximately 3.9 times 10 to the 12 newtons. Then secondly, explain how the gravitational force and the data in table 1 show that the comet is not in a circular orbit around the sun. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's only 1 mark, so you see it's a very straightforward calculation. And we know that the equation to work out the gravitational force between two bodies is F equals gm1 m2 over r squared. You then check all your values. Now you'll notice as well that the mass of the sun is given to you in the equation book for the exam. Pop all the numbers in and you should get 3.88 times 10 to the 12 newtons. Now the second one is asking for you to comment if it's in a circular orbit or not. Now you've already done a topic on circular motion for paper 1, and you know the standard equation to work out the centripetal force for any object going in a circle. So you can have either F equals m omega squared r or F equals mv squared over r. Now you'll notice that table 1 gives you v, so you should be using the equation F equals mv squared over r. Work it out and you should indicate that the two forces are not the same, so therefore that tells us that the gravitational force is not acting as a centripetal force, so therefore it's not in a circular orbit. The next question says, the orbital period t of an object orbiting the sun at a mean orbital radius r is approximately given by t squared equals kr cubed. Now the mean orbital radius of the comet is 18 re, where re is the mean orbital radius of the Earth. Estimate in years the orbital period t of the comet. Then the total energy of the comet is the sum of its kinetic energy and its gravitational potential energy. Show that the total energy of the comet at P is approximately minus 6 times 10 to the 21 joules. Then calculations for a different comet show that has a total energy of plus 6 times 10 to the 21 joules at its closest point to the sun. A student suggests that the comet will not remain in orbit around the sun. Discuss whether this suggestion is correct. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, as you know, you've got a constant there, so what you can do is remove the constant but say t squared equals r cubed for the comet and t squared equals r cubed for the Earth, and you can ratio them, and you can say t squared of the Earth over t squared of the comet is equal to r cubed of the Earth over r cubed of the comet. Now you have all those values because you know that the time in years for the Earth is 1, and because you're using a ratio, you do not need to convert it into seconds. You know what the radius, or so the distance between the Earth and the Sun is, the radius of the Earth's orbit, because it's given to you in the equation book, and you also know the distance between the Sun and the comet. So with that, you can work out your value for time t, and it is 76 years. Now in this next question, you've always got to remember that the total energy of a comet is its kinetic energy plus its gravitational potential energy. So you can work out the kinetic energy with a half mv squared, and the gravitational potential energy is minus gm1 m2 over r squared. Firstly, you can't use mg delta h because g is changing over the distances, so you can't use that. And remember, it's got to be a negative value because potential is considered to be a negative, as we'll get into in the next question. So you add the two, you work each one out, you add the two values together, and you should get approximately minus 6 times 10 to the 21 joules. Now, the next question, it's going to indicate that the comet will not remain in orbit around the sun. Now, why is that? Well, like we said before, we always have gravitational potential energy as a negative value. The reason why that is the case is because we say that the gravitational potential energy at infinity, which is outside of the gravitational field, anywhere outside the field, is equal to 0. So this is telling us that if you have to have 0 energy, for gravitational potential energy to be outside the field, it has to be at 0. So if it's at plus 6 times 10 to the 21, it's above 0. So therefore it has more than enough energy to reach infinity and to escape the gravitational field, so it will not be in orbit around the object. The next question says, show that the total energy E of a satellite orbiting the moon is given by the equation E equals minus gmm over 2r, where small m is the mass of the satellite and big M is the mass of the moon and r is the orbital radius of the satellite. Then explain the significance of the negative sign in the equation before. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, you've got to indicate that the total energy of an orbiting body is the gravitational potential energy and the kinetic energy. Now again, remember that the gravitational potential is a negative value, so you would have a half mv squared minus gmm over r squared. Now what you can then do is you can also rearrange this to equate the two, because one's a negative. So what you can therefore do is then rearrange your equation to have kinetic energy is a half mv squared, and it also equals gmm over r squared. So therefore we can just simplify it and say the kinetic energy is g big M small m over 2r. You can then add the gravitational potential energy to get the equation out as shown above. Now what's the importance about the negative sign? Well, it's the idea that the satellite needs energy to get to infinity, and we set infinity to be 0, so if it's inside the gravitational field, if it's orbiting the body, it must have an energy less than 0, so it must be a minus. So remember again that the bound system, when it's in an orbit around a object, when it's in the gravitational field, it must have a negative value because it is attracted to another object. Or you could just talk about in terms of total kinetic energy, that the idea that the kinetic energy is going to be less than the negative gravitational potential energy. The next question says, the satellite has a mass of 1 × 10⁻³ kilograms and orbits the moon in a circular orbit. The mass of the moon is 7.3 × 10⁻22 kilograms. Determine the orbital speed of the satellite when the orbital radius is 1.95 × 10⁻³ kilometers. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to be aware of how you can work out orbital speed. Now you can work out the orbital speed by equating the equations of the centripetal force, okay, to the gravitational force and make V the subject, or you could just memorize the equation, which is V equals the square root of gm over r. Now remember, the escape velocity is square root of 2gm over r, so don't get those confused. You know the gravitational constant is given to you on the equation sheet. You've got big M, which is the mass of the object producing the gravitational field, which in this instance is the moon. You then divide it by the distance between the center of mass of the moon and the center of mass of the satellite. Remember, they give you that value in kilometers, so you convert that into meters by putting that times 10 to the 3 again, so it'll be 1.95 times 10 to the 6. Pop all the values in and you get 1.58 times 10 to the 3. The next question says, the satellite's thrusters exert a force in the direction opposite to its direction of motion as shown in figure 5. This causes the radius of the orbit to decrease. Explain with reference to energy why the use of thrusters reduces the radius of the orbit, and then calculate the work done by the thrusters in reducing the radius of the satellite's orbit. Assume that the final orbit of the satellite is circular. So pause the video now, then unpause the video when you want to go through your answers. Right, so in answering this question, you've got to pay very close attention. It says with reference to energy, so you can't be discussing about forces, because even if it's correct, you won't get the full marks. So it's the idea that the thrust is in the opposite motion is opposite to the motion, so therefore work is being done on the object to reduce its gravitational potential energy. We then know from the gravitational potential energy that the value, that radius is in there, because it's minus gmm over r. So therefore it tells us that the thrusters will reduce the radius of the orbit. Now, how do we then work out the work done? Well, we work out the difference in the total energy by doing the equation we had before, which gave us the total energy, which was minus gmm over 2r. You work it out in both places, so you work it out with r in those different values. You then subtract one from the other. Now remember, we're minus and a minus, so we're going to be getting a plus. So it's going to be 6.7 times 10 to the 7 joules. We're now going to look at some questions regarding electrical fields. So this question says electrostatic precipitators are used to remove smoke particles from the gases released by coal-fired power stations. Figure 5 shows a simplified electrostatic precipitator. A metal rod of radius A is placed along the vertical axis of a hollow metal cylinder of radius B. Point X is halfway between the rod and the cylinder wall. The rod and the cylinder are connected to a high voltage supply to create an electrical field inside the cylinder. The electrical field strength E is horizontal inside the cylinder. Gases containing smoke particles enter at the bottom of the cylinder. The smoke particles become charged and attracted to the cylinder wall. The smoke particles stick to the inside of the wall and the gases leave at the top of the cylinder without the smoke particles. Figure 6 shows the variation of the magnitude of E with the radial distance r from the surface of the rod to the cylinder wall. The rod is at an electrical potential of minus 3.0 kilovolts and the cylinder is at 0 volts. A student suggests that potential at X is minus 1.5 kilovolts. Discuss this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Now again, with these types of questions, they give you the graph in the question, so it's going to ask you to reference the graph in your answer. So it's the idea that the area between A to X is much larger than X to B, so what we're saying is it's not going to be directly proportional, it's not a straight line down, so this tells us that the electrical field is not going to be uniform. In fact, it's going to be more likely to be a radial field. So it indicates to us that the midpoint is not going to be halfway between the smallest and the largest value. It would be the case if it was a uniform field, but it wouldn't be because it's not acting as a uniform field. The next question says a smoke particle enters the cylinder near the rod. Initially it is uncharged and travels vertically with a velocity of 5.2 meters per second. Figure 7 shows the path of the smoke particle inside the cylinder. The mass of the particle is 2.7 times 10 to the minus 17 kilograms. The particle acquires a charge of minus 3.2 times 10 to the minus 19 coulombs near the rod. The particle experiences an initial horizontal acceleration of 91 meters per second squared due to the electrical field in the cylinder. Determine the magnitude of E at the point where the particle acquires the charge. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you'll notice straight away you've got a horizontal acceleration and you've got a mass. So the equation that sticks out to me is the equation F equals ma. So we can use F equals ma by multiplying 91 by 2.7 times 10 to the minus 17 kilograms. That then gives us our resultant force, and then we know that resultant force is the electrical field strength times by the charge. So as a result, we can then multiply by the charge given in the question, and we can work it out to be 7.7 times 10 to the 3 newtons per coulomb. The next question says the vertical component of the velocity of the particle remains constant at 5.2 meters per second. Assume that all of the forces on the particle are negligible except the electrostatic force. State and explain any change to the magnitude and to the direction of the acceleration of the particle as it moves along its path. Refer to figure 6 in your answer. Then calculate the speed of the particle as it reaches the cylinder wall. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's asking about the idea to the change of the magnitude and the direction of the particle as it moves along the path. So when you're looking at figure 6, which was the graph, you've got to consider about the electrical field strength. Now we've just looked at an equation which said F equals EQ. Now from the graph you'll have noticed that E gets smaller, it decreases in size, decreases in size, decreases in size, because it's most likely a radial field. So if E is decreasing in size, well then the resultant force is decreasing in size, so therefore a resultant force causes acceleration, so the magnitude of the acceleration decreases. Now we'll notice that the direction of the acceleration hasn't changed. There's been no alteration to the direction of the force or to the electrical field strength's direction as such, so therefore the electrical field's direction, sorry, not the field strength but the field's direction, so therefore the direction doesn't change but the magnitude does. And so you can answer both of those points in that question. Now the next one, you're going to have to work out the speed of the particle. Now what you've got is, we know we've got the potential difference. How do we know that? It's from the diagram as shown, and we've got the charge from the previous question. So we know that the work done on the particle is going to be the potential difference multiplied by the charge, so 3 kilovolts or 3000 times by 3.2 times 10 to the minus 19. Now we know the initial kinetic energy of our particle is a half mv squared, and we can work that through to be 3.6 times 10 to the minus 16 joules. You can then add the work done because it's being accelerated, so therefore it's going to gain in kinetic energy. So you add the two together to get your total kinetic energy. Then what you can do is now you've got your total kinetic energy by adding the two values together, and then you can work out V by doing kinetic energy is half mv squared, rearrange it, make V the value, and work out your answer that way. We're now going to look at some questions regarding capacitance. So a student uses the circuit in figure 8 to determine the capacitance of a capacitor. The capacitor is initially uncharged. The variable resistor R is set to its maximum value and the switch is closed. R is then used to keep the charging current constant while the capacitor charges. The charging current is 0.3 milliamps, and during the experiment the student gradually decreased the resistance of R to maintain a constant current of 0.38 milliamps. The reading V in the voltmeter is recorded every 10 seconds for 120 seconds. The time is measured using a stopwatch. The battery has an EMF of 6 volts and a negligible internal resistance. So calculate the maximum resistance of R, explain why the resistance of R needs to be decreased to maintain a constant current, and then show that the charge on the capacitor after 120 seconds is approximately 0.046 coulombs. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's very important to note that all these questions are 1 mark only, so you're going to be using quite basic equations or quite simple statements in your answer. Now, to work out resistance, we know resistance is V over I. Now we want the maximum resistance, and because we know current is a constant, it's 0.38 times 10 to the minus 3, because milli means 10 to the minus 3, we've got to use our maximum value of potential difference, which is going to be the EMF of the source, which is 6. So it's 6 over 3.8 times 10 to the minus 4, which is 1.6 times 10 to the 4. Now in our next question, it's the idea that the potential difference across the capacitor is increasing as it's charging because it's building up that difference in charge across the both plates. So therefore the potential difference across the variable resistor is decreasing, so that will cause a current to go down because you need that push, that potential difference to push the charge across and to maintain that current. So therefore we're going to decrease the resistance to maintain that constant current. Now in this last one, we've been given the current and the time. So the obvious thing to work out is the charge by doing Q equals IT. We know that milli means 10 to the minus 3, so it's 3.8 times 10 to the minus 4 multiplied by 120 seconds to get 0.0456 coulombs. The next question says figure 9 is a graph of the voltmeter readings V against time t. Determine the capacitance of the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this particular question? Well, we know that capacitance is going to be Q over V, so you can't work it out from the gradient of the line, but what you can do is you can take values from the graph. So what you can do is take a reading from the graph to obtain the value of V after 120 seconds. So you're going to get between like 5.5 and 5.7 volts from how you've read that particular graph. You can then use the equation capacitance equals Q over V, and then we'll know what our charge is because we've just worked out in the previous question, divided by our value for V, and we get 8.1 times 10 to the minus 3 farads. The next question says the student makes a new capacitor as shown in figure 10. The two square metal plates have sides of length 15 centimeters. They overlap completely and are separated by a piece of dielectric material. The dielectric material has a thickness of 3.5 millimeters and completely fills the space between the plates. The capacitance of the capacitor is 0.13 nanofarads. Calculate the relative permittivity of the dielectric material and discuss whether the student could use the experimental procedure described previously to confirm the capacitance of the 0.139 nanofarad capacitor. So pause the video now and then unpause the video when you want to go through your answer. Right, so in this first question, we should be aware that to work out the relative permittivity of the dielectric material, we've got to use the parallel plate capacitor equation, which is C equals E0 ERA over D. So you can rearrange that to make E0 the subject, sorry, ER the subject, my apologies, by saying ER is equal to C times by D over E0 times by A. Now E0 is a constant given to you. You can work out the area by doing 15 times 10 to the minus minus 2 times by 15 times 10 to the minus 2 to work out your area. Remember again, you need to be converting from centimeters into meters. You can then also use the idea that the separation is 3.5 millimeters by having d is 3.5 times 10 to the minus 3 to get our answer out to be 2.3. Now you should have noticed for the question 6 that it's a nanofarad capacitor, and the previous one was not a nanofarad, it was much higher capacitance. So what this tells us is that this new capacitor has a really much smaller capacitance than the previous capacitor. Now I like to visualize capacitors as holding like jugs of liquid, like jugs of water. So this particular capacitor is a much smaller jug. It can hold a lot less water, a lot less charge. Now charging a capacitor is like pouring water into a jug. So we can, if we pour it at the same rate, it's going to fill up a lot faster, and most likely you're not going to get many measurements because the current would very quickly reach zero. It would become the capacity completely full of charge, okay, before you had to take your readings with every 10 seconds. So it just would not work. So the potential difference across the capacitor would reach 6 volts before you could take your readings with the stopwatch. We're now going to look at some questions regarding thermal physics. So the first question says, figure 1 shows a boiling tube containing melted wax at 85 degrees Celsius. The boiling tube is in a beak with cold water. The temperature of the wax is recorded every minute for 16 minutes. Figure 2 shows the results. So estimate using figure 2 the melting point of the wax. Then the internal energy of the wax decreases at an average rate of 7.8 joules per second during the time the wax changes state. Estimate the mass of the wax in the boiling tube. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know that you change state, so the melting point will be when you have a straight line on a temperature time graph. So you look across and the straight line is occurring between about 80.2 to 80.4 degrees Celsius. When I say straight line, I mean flat line. Now the next one is we can now use this to work out the mass of the wax in the boiling tube, because the latent heat is the amount of energy per kilogram you need to melt it in this instance. So we can say that Q equals ml, and then we can also say E equals PT. Now we know what the power is because it gives you in the question, because joules per second is power, it's a watt. So you do 7.8 times by the time it needed to melt, so you can read it off the graph where it starts to have a flat line to when it finishes having a flat line. Convert that time back into seconds from minutes, and you can work out your value for your energy, which is Q. Then you can rearrange it, say M equals Q, which you've just worked out, over L, which you just given, and then you get an answer between 0.022 to 0.025 kilograms. The next question says, describe how the average kinetic energy and the average potential energy for the wax particles changes between 8 and 16 minutes. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, you think when it's going from 8 minutes to 16 minutes, it's in the process of changing state, and then it decreases its temperature. So when it's changing state, the potential energy store of the object will decrease, because the state links into the potential energy store. So because it's changing state, and in this case it is melting, so therefore we're going to a substance which has particles further spread out, so the potential energy will go down. So the potential energy will decrease. The kinetic energy store is not linked to this because they are completely separate stores, so that stays the same. Now the temperature links to the kinetic energy store, so when the temperature is decreasing but the state is staying the same, well then the potential energy store will not change, but the kinetic energy store will go down because the object is decreasing in temperature. We're now going to have a look at some questions regarding magnetic fields. So figure 11 shows the path the proton takes as it travels in the Earth's magnetic field. The proton moves in a helix around the magnetic field line. The radius of the path is shown in figure 11, and the proton moves with a constant speed. The magnetic flux density in this region is 1.2 times 10 to the minus 7 teslas, and the velocity of the proton has two components of constant magnitude. The component perpendicular to the mag field is 450 kilometers per second, and the component parallel to the mag field is 120 kilometers per second. So the solar wind is a stream of highly energetic particles, okay, such as protons that flow out from the sun. So state the condition in which a charged particle moves in the magnetic field and experiences no force. The radius r is constant, and calculate r. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So how do you know it's experiencing no force? Well, in a magnetic field, a charged particle experiences no force if either it is stationary or it's moving parallel to the field line. So it must be, because it's moving, must be moving parallel to the field line. Now, work out the value of R. Well, straight away you know you've got B, you've got Q, and you've got V. So you can work out what the force is by doing F equals BQV. Now, importantly, what value are we using for V? Well, we're not going to be using the value parallel to the magnetic field, because that will not be relevant in this case. So you've got to use the perpendicular velocity, which, if you can see on here, is 450 kilometers per second. We don't work in kilometers per second in physics, we work in meters per second, so we convert that to 4.5 times 10 to the 5 meters per second. That allows us to work out F, and we know that it's moving in a circular path. So because we know it's moving in a circular path, as we can see here, it's moving in a helix, okay, we can use the centripetal force equation of mv squared over r. We're linking our two topics together. We've got the mass, we've got the force, we've got the radius of the orbit, so therefore we've got the speed, so we can work out the radius of the orbit to be 3.9 times 10 to the 4 meters. The next question says, explain why the proton takes the path as shown in figure 11. Then the interaction between the solar wind and the Earth's magnetic field can cause a small change in the magnetic flux density near the Earth's surface. Explain how this small change can cause in the induction of very large voltages in power transmission lines. Refer to Faraday's law in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So like we mentioned before, it's very important to note that the parallel component of the velocity is unaffected by the magnetic field, because it works perpendicular to the velocity. So the magnetic force is the centripetal force, and the centripetal force will always act perpendicular to the motion of the object. So therefore the centripetal force will cause the circular motion. Now, in the second question, it's so important you actually reference Faraday's law. So what is Faraday's law? It's that the EMF is directly proportional to the rate of change of magnetic flux linkage. So we must be achieving a high EMF, because it indicates that in the question of an induction of a very large voltage. So that can only be achieved by a very, very big change in the rate of flux linkage. So that happens because you've got a very large area, because we know flux linkage links into the magnetic field strength and it links into the area of the object, because our power cables are so long, as indicated in the question. The next question says, describe what is necessary for a charged particle to experience a force due to its movement in a magnetic field. Then show the radius of a circular path of a charged particle in a uniform magnetic field in a vacuum is given by the equation R equals P over BQ, where P is the momentum of the particle, B is the magnetic flux density, and Q is the charge of the particle. So pause the video now, then unpause the video when you want to go through your answer. Right, for this first one, you've got to just remember this key idea, and it experiences a force when it has a component of its velocity perpendicular to the field. So it's important to note that the velocity and the magnetic field are perpendicular to each other. If it was parallel, it would experience zero force completely. Now, how do you do the second question? Well, what you do is you remember that the magnetic force here, which is F equals BQV, is going to therefore be equating to the centripetal force, because it's causing the object to move in a circular path. So we can say mv squared over r equals BQV. We can then rearrange that, make r the subject. Remember that momentum is mass times velocity, so P equals mv, and we get our answer out to be r equals P over BQ. The next question says, a cloud chamber is a particle detector that produces visible tracks. The tracks form as charged particles ionize air molecules along their paths. Charged particles produce spiral tracks when the cloud chamber is placed in a uniform magnetic field. Figure 11 is a full-sized image showing the track of a particle created at point X in a cloud chamber. The particle travels in a horizontal plane, and the magnetic field direction is into the plane of the page. Explain why the radius of the path decreases as the particle created at X travels through the cloud chamber. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So it's important to note that as it's going through the cloud chamber, it's colliding with the particles in the chamber. So therefore, it's going to lose some of its kinetic energy as it whacks into them. Now, the particle's velocity will therefore decrease, its momentum will decrease. And we've just looked at our previous equation that says R equals P over mv. So that tells us, when you work it through, not R equals P over mv, if you look at the previous question, R equals mv over bq. So R equals P over bq. So what that indicates to us is that the radius of the orbit is directly proportional to the velocity and the momentum. So therefore, if the momentum decreases and if the velocity decreases, well, therefore the radius will decrease as well, showing the path in the figure. The next question says, a gamma photon produces two particles in a pair production event in the cloud chamber. Figure 12 shows the tracks due to the pair production event. Explain what figure 12 indicates about the three particles involved in the pair production event. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question to link magnetic fields and particles, because that's how particles were first discovered and understood in the 1950s and 1960s. So because our particles have spirals in opposite directions, that tells us straight away that the charges of the two particles produced in the pair production event are opposite because their spirals are in opposite directions. But they must have the same momentum, so most likely the same mass and the same velocity, but just in opposite directions, because the tracks have a similar radii. So therefore we know that R equals mv over bq. So if R is the same, mv must be the same. Now finally, if you look on this picture, you'll notice that there's no track before the event takes place. Now you should remember from paper 1 that pair production is when a photon is then changed into a particle-antiparticle pair. Now that indicates to us that if there's no track beforehand, well then the photon beforehand, which must be present for a pair production event, must be very weakly ionized or very difficult to detect because there is nothing there in the chamber. There is no track. Let's now have a look at some questions on nuclear physics. So the first question says, FDG is a chemical used in medicine. FDG contains the nuclide fluoride 18. Fluoride 18 has a half-life of 6.59 times 10 to the 3 seconds. Firstly state what is meant by the half-life of fluorine 18. Then show that the decay constant of fluorine 18 is approximately 1.1 times 10 to the minus 4 seconds. Then a sample of FDG with an activity of 370 megabecquerels is injected into a patient. Assuming that the activity of the sample is due only to fluorine 18, calculating kilograms, the mass of fluorine 18 in the FDG sample. Then the sample of FDG was produced in 12 hours before it was used in the injection. Calculate the activity of fluorine 18 in the sample of FDG when it was produced. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to know what the definition of half-life is. And the half-life is the time taken for the activity or the mass or the number of radioactive nuclei in the sample to half or decrease by 50%. Now again, this next question is 1 mark, so you know it's going to be a very simple equation. So you know that the half-life is log 2 over the decay constant, so decay constant is log 2 over the half-life, so therefore you can pop it through and you work out your answer to be 1.05 times 10 to the minus 4. Now in this next question, it's a bit more challenging. Now we know we've been given the activity, and we know activity is equal to lambda n. Now we've just in the previous question worked out lambda, the decay constant, so therefore we can work out n. Now remember, 370 becquerels for the activity is 370 times 10 to the 6, because that's what mega means. So we can then use that value to work out n, which is 3.52 times 10 to the 12. That's how many particles that you have. So therefore you can then work out, okay, the mass in total by doing the n times by the atomic mass divided by Avogadro's constant. Now you know that the mass of 1 mole of fluorine is 1.8 times 10 to the minus 2 kilograms. So if you know how many particles there are, you can then work out how many moles you've got by dividing that value by Avogadro's constant, because it is how many particles are in 1 mole. And then when you know your number of moles, you can multiply by the number on the screen, 1.8 times 10 to the minus 2 kilograms, to get your total total mass to be 1.1 times 10 to the minus 13 kilograms. Now in this last question we've got a time and we've got an activity, and we want to work out our initial activity. So we say A equals A0 e to the minus lambda t. Remember, t has to be in seconds now, so 12 hours will have to be converted into seconds by doing 12 times by 60 times by 60. And then what we can do is make A0 the subject, A0 being the activity at the start. So we can say A0 is going to equal A over e to the power minus lambda t. We've got lambda, the decay constant from the previous question. We know what our value of A is 370 times 10 to the 6. We can pop our values in and we get 3.5 times 10 to the 10 becquerels. The next question says, state and explain one practical problem in achieving fusion in reactors. The equation below describes a fusion reaction that occurs in the Sun, and table 2 shows the mass of each nuclide. Calculate in joules the energy released in this reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you've got to realise there are three problems with fusion in nuclear reactors on Earth currently. Firstly, you could indicate that it's difficult to achieve the high enough temperatures and pressures in the plasma to constantly have fusion working at a consistent rate. Secondly, you could indicate that extracting the energy from the plasma after it's being produced is a very cost-effective process. Is not a cost-effective process, sorry, and actually you don't have an energy surplus after this. You actually have an energy deficit. And then finally, the idea that neutrons are produced in this fusion process and they've got a high energy, so are likely to be ionizing, which will be an issue. Now in this next question, we want to use our equation delta E, the energy difference, the energy released, is equal to delta M, the change in mass in before and after the reaction, times by C squared. So what you do is you work out your total mass before by adding the mass of 3 helium plus 4 helium. You then find the mass of the beryllium afterwards to find the mass afterwards. You then calculate your mass difference. You then multiply it by C squared to get your energy in joules, and you should be getting 2.6 times 10 to the minus 13 joules. The next question says, uranium fuel rods used in a thermal nuclear reactor contain uranium-238 and uranium-235. Table 3 gives the mass of a uranium-238 nuclide and a uranium-237 nuclide. Deduce whether a uranium-238 nucleus can decay into a uranium-237 nucleus and a neutron. Then describe how a chain reaction occurs in the uranium-235 fuel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to understand that a decay process, you have to lose mass ultimately, because some mass is converted into energy. So you find the mass between the 238 uranium, and then the mass of the 237 uranium plus the mass of the neutron is given to you on the equation sheet. And then you notice that the decay cannot happen because actually the 237 uranium plus a neutron has a higher mass than the uranium 238. So therefore that decay cannot take place. Now the second question is explaining how a chain reaction occurs. Now the important thing to note is you've got to be aware that a chain reaction is caused by a neutron being absorbed by a uranium nucleus and causing fission from that process. Now it's only the uranium-235 that can absorb this neutron and then cause fission, and then the fission process itself will produce more neutrons between 2 and 3 for every nucleus, which will then go on to fission other nuclei. The next question says, state one substance that is used as a moderator in a thermal nuclear reactor. The neutrons required to produce fission in many reactors are thermal neutrons. State why they are called thermal neutrons. Then explain why the kinetic energy of the neutrons needs to be reduced for the chain reaction to occur. And neutrons lose kinetic energy by a series of collisions with nuclei of the moderator. Each neutron keeps an average of 84% of its incident kinetic energy in each collision. One neutron has an initial kinetic energy of 2 times 10 to the 6 eV. Deduce the average number of collisions the neutron makes to reduce its kinetic energy to 2.5 times 10 to the minus 2 eV. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, it's just a fact you've got to learn. Either water or graphite. Both of those are used as moderators in nuclear power stations in the UK. Now we call these neutrons in the process thermal neutrons because they have collided with the fission products and removed energy, kinetic energy from those products. So ultimately after the collisions they're in thermal equilibrium with the fuel and the moderator because they have collided so many times they have the same amount of kinetic energy. Now why does kinetic energy need to be reduced? Well, it's the idea that we need the neutrons produced in the fission process to cause fission in other nuclei, okay, and at least more than one in each event does that. Now, the idea that the neutron will be accepted by the nucleus depends on its kinetic energy. So the faster neutrons are less likely to be absorbed and therefore by the uranium-235 nuclei, and to therefore induce fission. So reducing the kinetic energy increases the probability of acceptance into the nucleus and fission being taken out place. Now this last question, question 6, is all about mathematics. Now when you're losing a percentage or keeping a percentage of energy in each collision, you can work it out by multiplying the value you're keeping it by the number of collisions. So in this case it's 84%, so it's 0.84. So you can see we're multiplying the value by 0.84 to the power of n. So we can say the final value is equal to the initial times by the percentage kept times to the power of the number of collisions. So it's 2.5 times 10 to the minus 2 equals 2 times 10 to the 6 times by 0.84 n. We can then rearrange it, make n the subject. Remember, if you've got exponentials, you can use logs when you're rearranging that to get 105 out. Now the next question says, liquid sodium is used as a coolant in some types of nuclear reactor. Table 4 gives some properties of sodium. Now calculate the energy required to heat 3.3 times 10 to the 5 kilograms of sodium from an initial temperature of 20 degrees to a final temperature of 560 degrees Celsius. And then during the operation of the reactor, radioactive cesium-137 is produced. The cesium-137 is removed from the reactor as waste which needs to be stored. Cesium-137 decays into stable barium-137 with the emission of a beta particle and gamma radiation. The half-life of cesium-137 is 30 years. Outline the problems associated with the storage of this waste. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you're given lots of information, but what stands out to me is that you've got the average heat capacity of the solid and the average heat capacity of the liquid and the latent heat of fusion. So it's important you have to work out the energy required to heat it up from 20 to 98 degrees, and that's going to be the average heat capacity of the solid multiplied by the mass, which we're given to be 3.3 times 10 to the 5, multiplied by the change in temperature, so 98 minus 20. That gives us that energy. We can then work out the energy when it's changing state by saying E equals ml. We've got the latent heat of fusion. Now be careful in all these values, by the way, they give you the kilojoules, so you need to convert the latent heat and all the heat capacities into joules by multiplying by 10 to the 3. So you multiply the mass by the latent heat of fusion, and then finally do the heat capacity when it's a liquid, so do MC triangle T, which is going to be from 98 to 560. And then doing it by the heat capacity of the liquid. So you do all those values, you work them all out, you then got to add them all together because we're working out the total energy. So you work out all three and you get 3.09 times 10 to the 10, 1.98 times 10 to the 11, and 3.63 times 10 to the 10. Add them all together to get 2.65 times 10 to the 11 joules. Now in this last question, you will be tested or asked to know about how you can store nuclear waste. So from looking at the information given in the question, you've got to link to the idea that there's going to be high energy particles released, which could be ionizing. So you've got to think about how you can shield the radiation so it doesn't release these particles around people. So you can think of having like a shield, like a steel or lead or very thick concrete wall, and also you could have maybe possibly being in water to shield it and also to cool it. The other idea is that the half-life of cesium is 30 years, so you'll need to store it for a very long time. Now the general rule in radioactivity is to store it for at least 5 half-lives, so it's down to a very small percentage of its initial value. So you'd say you'd have to store it for at least 150 years because one half-life is 30 years. So look at answering some questions on the topics from paper 2 in A-level physics. So the first questions are going to be on gravitational fields. So the following question says, the lines in figure 4 show the shape of a gravitational field around two stars, G and H. Compare with reference to figure 4 the masses of G and H, and then X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've got to remember that in a field, that the density of the field lines indicates the strength of the force, and in this case, the gravitational force is affected predominantly by the mass of the object that is present. So you can see that G must have a greater mass than H does, and why is that? Because there's two things you could possibly say. You could possibly indicate that the density of the field lines is greater around G compared to H, or you could say that the null point, the point at which the two gravitational fields will cancel each other out, is closer to G than it is closer to H than it is to G, so therefore G must have a stronger field than H. Now again, the other fact you've got to remember about gravitational fields is that the field lines point in the direction a point mass would take. So therefore, for both of them, it would indicate towards the actual object. Because it's a gravitational field, it's always an attractive force that's going on for gravity. So therefore, the masses will always be going towards the two objects. So therefore, the field lines should be pointed towards the actual object. And it's important that they're given tangential arrows as well. Now the next question says a spherical asteroid P has a mass of 2 × 10 to the 20 kilograms. The gravitational field strength at its surface is 0.40 newtons per kilogram. Calculate the radius r of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, if you look at your equation sheet given for your examination, you are aware that you can work out the gravitational field strength little g by doing little g equals big G m over r squared. So we can therefore rearrange this and make r the subject by saying r is equal to the square root of gm over g. You've then got the value of the gravitational constant from your equation sheet, you've got the value of the mass in the question, and you've got the gravitational field strength little g in the question as well. So you pop in all the values, you work it through, and you get 1.8 times 10 to the 5 meters. The next question says, sketch on figure 5 the variation of the gravitational field strength G with distance r. The distance r is measured from the centre of P. Then explain what is represented by the area under the graph between r equals r and r equals 2r on figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, it's important to note that you should be aware that for these objects that the gravitational field strength will vary as a radial field, so therefore it's going to be sketching across like so. Now again, you'll be aware that as the distance doubles, well therefore the field strength is going to go down by a factor of 4 because it's related to r squared. So when one is double, the other is gone by the power of 4. Now we know that at a distance of r that the field strength is 0.40 from the previous question, so therefore at 2r it's going to be 0.4 divided by 4, so it's 0.1, and then you can do for 3r, so then you can divide that by a factor of 4 as well, okay, so you can work it through like so. Sorry, that would be for 4r. For 3r, what you would do is you go from r to 3r, you then go by a factor of 9 because it's 3 squared, so it'll be 0.4 divided by 9, which is 0.044. So you can plot those points in there and sketch the line in. Now, what is represented by the area? Well, again, there's a couple of answers you could say. So you've got to be aware that in these graphs that the area under the line represents the energy transferred or the work done per unit mass, or that is, in essence, the gravitational potential. So therefore, if we're thinking in terms of energy per unit mass, it's the energy transferred or work done on an object per unit mass to move from r to 2r. Or you could say it's the increase in gravitational potential moving from r to 2r. Again, remember how to work out values from graphs. The next question says, asteroid P approaches the two stars G and H. Figure 6 shows one position of P close to H. The gravitational force on P from G is 6.38 times 10 to the 12 newtons. The mass of H is 3.00 times 10 to the 25 kilograms, and the mass of P is 2.00 times 10 to the 20 kilograms. The distance HP is 1.50 times 10 to the 11 meters. Calculate the magnitude of acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, you know straight away that it's worth 4 marks. It's going to be either a double step calculation or a challenging calculation that you're given. Now you have the gravitational force, you have the mass of two objects, and you have the distance between the two. So what you can therefore do straight away is say F equals gmm over r squared. So what you can then do is work out that value of the force. So you can find the force between P and H. So therefore you can say, well, the force between P and H is 6.67 times 10 to the minus 11 times by 3 times 10 to the 25 times by 2 times 10 to the 20 all over 1.5 times 10 to the 11 squared. So therefore gives you an answer of 1.8 times 10 to the 13 newtons. So what we've got here is we've now got the two components of the gravitational force, the one from P to G and the one from P to H. So as a result we can work out the total by using a bit of Pythagoras and saying that the total is going to be FPH squared plus FPG squared all square rooted. So we do those two and we square both values, add them and square root them to get the total value of F to be 1.9 times 10 to the 13. At that point we know acceleration. Well, we've got the masses, we know the force, so we therefore know acceleration is the overall force divided by the mass. We've just worked out the overall force to be 1.9 times 10 to the 13. We can then divide it by the mass, which is 2 times 10 to the 20, to get our answer to be 9.4 or 9.5 times 10 to the minus 8 meters per second squared. We're now going to have a look at some questions to do with the electrical fields topic. So figure 7 shows two identical negative point charges, QA and QB, in fixed positions 8 millimeters apart. O is a point midway between the charges, P is a point 3 millimeters away from O, and equidistant between QA and QB. Firstly, the resultant electrical field strength at P is 1400 newtons per coulomb and towards O. Calculate the charge of QA. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, a couple of things. Firstly, what do we know that the equation is for the resultant electrical field strength? Well, we know from the equation sheet that E is equal to Q over 4 pi epsilon 0 r squared. But what we also know is from our setup, from our diagram, we can also say that the resultant electrical field strength is going to equal 2E cos theta. So what we can do is we can work out what E is going to be by using that equation of Q over 4 pi epsilon 0 r squared. We can then link that into we can work out from the equation of E resultant is equal to 2E cos theta. We can therefore link that into work out E, and therefore what we can do is we can then work out one of the charges by using that equation E equals Q over 4 pi epsilon 0 r squared to work out our value. So you can work that all through using trigonometry to work out what cos theta is going to be, and then you can work it out and you get Q equals 3.2 minus 3.2 times 10 to the minus 12 coulombs. The next question says, sketch on figure 8 the variation of electrical potential V with displacement x from O between QA and QB. Calculations and numerical values of V are not required. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that the electrical potential will always be a negative value, and that's a very important idea because they're attracting each other. So at that point we know it's going to be a negative value. So at that point there's going to be a smooth curve, which is always negative, and there's going to be a non-zero maximum at the y-axis, and it's going to be asymptotic at about 4 and minus 4. The next question says, figure 9 shows a point R between O and QB. QA and QB are fixed positions. A small mass M with a negative charge Q is released from rest at R. Only electrostatic forces act on M. After release, M oscillates about O along the line between QA and QB. State and explain how the direction of the resultant force on M varies during oscillation. Describe the energy changes of M from its release until it reaches O for the first time, and then deduce whether or not M performs simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is a very standard question for paper 2 because it links two topics together, the electrical field strength and simple harmonic motion. So you should know for the first one, state and explain how the direction of the resultant force on M varies with the oscillation. Well, the direction is always acting towards O. That's because the idea that the Q charges will both repel M, and therefore the nearer it is to Q will repel more, so therefore it will always be attracted to O. Now, in terms of what's happening, it's going from electrical potential energy because it's moving due to the repulsion in the charges. Okay, so it's transferring to kinetic energy because it's now moving due to this repulsion. Now, again, to get that second mark, you've always got to indicate how the energy changes will take place. So a decrease in electrical potential energy will be equal to an increase in the kinetic energy. So when it goes from one store, it will go towards the other store. Now, the last one, will it perform simple harmonic motion? Well, this is actually a link to the idea of what simple harmonic motion is. So simple harmonic motion comes from the idea that the acceleration is directly proportional to the displacement in the opposite direction. Now, you should know that the electrical field strength and the electrical force will link as 1 over r squared. So therefore, it's not going to be directly proportional to distance because it's over distance squared. So therefore it will not be simple harmonic motion. We're now going to look at questions on the capacitance topic. So the first question says, state what is meant by a capacitance of 37 millifarads. Then a capacitor is made up of two parallel metal plates which are separated in air by a distance d. A cell of negligible internal resistance is connected across the capacitor as shown in figure 10. Switch S is closed and the capacitor becomes fully charged. While S is still closed, the plate separation is reduced to d over 2. State and explain what happens to the magnitude of the charge stored by the capacitor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, this first question, you've got to learn how to just define what we mean by capacitance. So capacitance is the charge stored per unit volt. Now, in this case, it's 37 millifarads, so therefore it's 37 millicoulombs stored per unit volt, or per 1 volt. Now, in the next question, what's going to happen to the magnitude of charge stored by the capacitor? Now, again, you've got to link it to the equation. Now, the equation for capacitance is that capacitance is going to be equal for a parallel plate capacitor to E0 ER A over D. Now, again, we can consider E0 and ER to be the same value in this instance because we're not changing any of those terms. So therefore, capacitance is going to be linked to A over D. Now, again, we know that Q is equal to CV. So we know straight away that the capacitance has doubled. We know that the potential difference or the voltage has stayed the same. We're told that from the question. So therefore, Q must have to double because we're linking it into, therefore, that separation. You can see how they all link together in their different equations. Now, the next question says, explain how charge is conserved when the plate separation is reduced. S is now opened. The plate separation is increased to D. And state and explain how the energy stored in the capacitor changes during this process. And then explain how energy is conserved when the plate separation is increased as described in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So, in this first question, you've got to understand that charge is conserved because there's an equal number of electrons removed from the positive plate as deposited onto the negative plate. Remember the idea that there's always two plates. One is where the electrons are removed, okay, and they are the ones from the positive plate, and the electrons are going onto that negative plate. Now, what's going to happen in the next question? So again, what will we do? Well, we know again that charge is going to stay the same because the capacitor is isolated, or that the charge can't flow because the switch is now open, so the charge can't flow around the circuit. So at that point it tells us that the capacitor halves, because we know that the capacitance halves, because you know E equals Q squared over 2C. So therefore at that point we can tell that energy doubles. So you can even say this qualitatively, but you can't get enough marks for this. The idea that work has to be done to that external system, to the capacitor, to separate out that plus and minus plates. So therefore energy must be stored in the capacitor because we're putting energy into it to actually separate those two plates out. So we know that from the previous one that links into the equations. Now how is energy going to be conserved? Well, the idea of energy is conserved because the gain in stored energy is provided by work being put into the capacitor to separate the plates apart. So work is being put in, energy is being put in to that capacitor to actually physically separate those two plates from each other because they are attracting each other. Let's now have a few questions on thermal physics. So the first question says the volume of a fixed mass of gas is kept constant. Explain why the pressure of the gas decreases when the temperature is decreased. Then show that the pressure P of an ideal gas can be given with the equation P equals rho RT over M, where rho is the density, T is the absolute temperature, and M is the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So you've got to talk very qualitatively about what is going on. So the idea is that if we decrease the temperature, the internal energy of the gas will decrease, because for a gas, that the internal energy for an ideal gas is the thermal energy. It is linked to the temperature. So therefore what we can say is that the mean kinetic energy, or the speed of the particles, will decrease. So therefore if the particles are moving slower, the frequency of the collisions with the container, okay, now remember it's the frequency of the collisions, not just the collisions themselves, the frequency of the collisions will therefore decrease. So therefore the change of momentum that's occurring will decrease, and we know that that force is equal to change in momentum over time. So therefore if the change in momentum decreases, the force exerted will decrease. So therefore the pressure will decrease, because we know pressure is force over area. The area is unchanged, the force is reduced, the pressure goes down. Now the next question links to a lot of the previous equations you know for thermal physics. So we know that the number of moles is equal to M over M. We know that rho is equal to M over V, and we know that PV equals nRT. So what you need to be able to do is link those into the equation. So what you can do is start with PV equals nRT. We can then sub in M over M for N, or we can sub in that V is going to equal M over rho. The two small m's will cancel through. We've then got the big M left in the equation. As you can see, we've got rho left in the equation. We can rearrange to make P the subject, and we get out our value. The next question says, figure 3 shows the variation of pressure with temperature for a gas at a constant volume. The density of the gas is 1.6 kilograms per meter cubed, and assume that the gas is ideal. Determine in kilograms per mole the molar mass of the gas. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you consider answering this particular question? Well, when you're given a graph, you've got to be able to use it. So use a data point from the line of best fit, which is linking, as you can see, the pressure and the temperature. But you'll notice from the equation given, from the graph given, that the pressure is in megapascals, so you have to convert that, and the temperature is in degrees Celsius. Now, the ideal gas equation needs the absolute temperature, so you need to convert from degrees Celsius into Kelvin. So what you'll do is you'll convert the temperature into Kelvin. You'll convert the pressure into pascals. We'll then use our previous equation of P equals rho RT over M. We know R from the equation sheet because it is just a gas constant. We know rho from the information given in the question. You are told it. We've read off T and M from the graph, and therefore we can work it out to be 3.9 times 10 to the minus 2. Another way in which you can do it is you can determine the gradient of your graph, and you'll be aware that the gradient is going to be equal to rho R over M, because we know that it's pressure over temperature, which from the previous equation we can work it through. So we can then use that to work out what our value of kilograms per mole is going to be. Let's now have a look at some questions on the topic of magnetic fields. So the first question says, a student investigates the EMF induced in a coil of wire when it is rotated at a constant angular speed in a uniform magnetic field. An oscilloscope is connected across the output of the coil. Figure 1 shows the trace on the oscilloscope screen, and Figure 2 shows the time-based setting for the oscilloscope. Firstly, describe what the student should do to determine an accurate value for peak EMF induced in the coil. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you understand how to work out values accurately from an oscilloscope. So what you're firstly going to have to do is work out what the number of each vertical square means in terms of volts. So you can look on the right hand side and you can see that is in fact for the time base, so that's not going to be relevant in this case. However, what we can do is we can work out what the value is by looking at what our Y gain is going to be, our Y scale. Then what we can do is turn off the time base, and then what you can do is increase the Y gain or decrease like the volts per division setting, the Y gain, so the trace takes up more of the screen so it's easier to read off the value. At that point you want to work out the most accurate value. Now in science, in physics, to reduce your percentage uncertainty, to increase the accuracy, you want to take the largest value possible, and that reduces that value. So as a result, the largest value possible is not the peak voltage, but in fact it's the peak to peak voltage, the value from the top of the line to the bottom of the line. So you'd work out your peak to peak voltage and then divide by 2 to get that most accurate value. The next question says, show that the angular speed of the coil is approximately 13 radians per second using Figure 1 and Figure 2, and then Figure 3 shows the oscilloscope screen with the time base set to off. The student wishes to make an accurate measurement of the time period of the induced EMF. Calculate an appropriate time base setting and explain your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So how to work out the angular speed is you work out the number of squares for the multiple cycles, and then what you can do is you can therefore work out like 9.6 to 10 squares for 4 cycles. So therefore what we can do is work out the number of squares for 1 cycle. We can then work through by saying that the angular speed is 2 pi over t. So therefore we know 2 pi because it's just a number. We know t because we can work it out from the previous question, because we can work out the time needed for 1 period. Okay, again, it's more accurate to take multiple values and then divide by the number of values that you take to reduce your percentage uncertainty. So you should get an answer from about 12.7 to about 13.1 radians per second. Now again, the answer for this next one should be about 50 milliseconds per division, because what you want is you want your 1 cycle to fill the entire screen. So you've got to think, how would you work it through to get 1 cycle in there? So it's going to be that 50 milliseconds value from the information given in the previous question. The next question says, the peak EMF is 7.5 times 10 to the minus 2 volts. The coil has an area of 6.0 times 10 to the minus 3 meters squared and 25 turns of wire. Calculate the magnetic flux density of the magnetic field. And Figure 4 shows the coil connected to a 27 ohm resistor. The resistance of the rest of the circuit is negligible. Calculate the mean power dissipated in the resistor. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you should know from the equation sheet that the maximum induced EMF, the peak EMF, is equal to BAN omega. Now in the previous question we just worked out omega. You have got the value of area in the question and the value of N. So at that point we have peak EMF, we have A, we have N, we have the angular speed, so you can work out what B is, and we get 0.039 Teslas. Now in this next question again, what are we aware of? We've got the resistance, we know it's 27 ohms. Okay, and what we also know is we can actually work out what our value of V is. But because it's an AC generator, you've got to remember, or an AC motor, what you've got to remember is you've got to be using the value of VRMS, because you use VRMS and IRMS to work out values in alternating current circuits. So the first thing to do is work out VRMS. Now we have peak EMF or V0. So we can say V RMS is V0 over square root 2. That's again an equation given to you on the equation sheet. And at that point we can sub that into the next equation of P equals V squared over R. We've got R, we've just worked out V, so it's 1.0 times 10 to the minus 4 watts. So now what we're going to do is we're going to look at answering questions on nuclear physics. So the first question we're now going to look at is that a proton of 0.675 MeV of kinetic energy collides and fuses with a stationary nucleus of boron-11. An excited carbon-12 nucleus is produced. The excited carbon-12 nucleus de-excites to a stable carbon-12 nucleus by emitting a gamma photon. Calculate in MeV the energy of this gamma photon. Assume the carbon nucleus does not recoil when the gamma ray is emitted, and state your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So the first thing to note is you can see that from our equation we've got a proton and we've got the boron, and that then turns into the carbon nucleus or the carbon-12 nucleus. Okay, so the first thing we need to do is add the proton rest mass to the mass of the boron, and at that point we can work out what our mass defect is, or the difference in the masses between that and carbon-12, and then at that point we can then multiply our rest mass or the mass defect, which we have probably in U, by 931.5 MeV. Again, that's a conversion factor. You've just got to learn how to convert between U and MeV, which is by multiplying by 931.5, and at that point we've got our energy in MeV. We can then add the kinetic energy contribution by the proton, which we're told in the question is 0.675. So at that point we get 16.6 MeV, and then again we give our answer to three significant figures. Why is that? Because if you look in the question, the number of significant figures given for energy in this question is 3, because it's 0.675. So we give our answer to the same number of significant figures as the value given in the question, which is 3. So therefore it is 16.6 MeV. The next question says, an alternative mode of decay for carbon-12 is to decay into beryllium-8 nucleus and an alpha particle. The carbon nucleus is initially stationary, and the beryllium-8 nucleus and the alpha particle move as a result of the decay. Compare the momentum of the kinetic energy of the beryllium nucleus to the momentum and the kinetic energy of the alpha particle immediately after the decay. Ensure to support your answer with a calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that we need to conserve momentum in this particular collision, in this particular production. So therefore we know the carbon nucleus is initially stationary, so the positive momentum of one must equal the negative momentum of the other. So therefore we can say that the momenta are equal in magnitude yet opposite in direction. So at that point we know that the momentum calculation is that the velocity, therefore if the momentum is the same for both, well then the velocity of the alpha particle must be 2 times the velocity of the beryllium. We see that because we know that the mass times velocity of both must equal each other, and we know that that the mass of the beryllium is double that of the alpha particle from the information given 8 and 4. So at that point we know the velocity of the alpha must be double that of the beryllium. We know that kinetic energy is a half mv squared. Now we know that the mass of the beryllium is twice as much as the mass of the alpha, yet the kinetic energy, so the velocity of the other is twice as much as that. However, the velocity is squared, so one goes up by a factor of 2, the other goes up by a factor of 4, so therefore it'll cancel out to be a factor of 2 increase from the kinetic energy of the alpha compared to the kinetic energy of the beryllium, because that velocity is squared. The next question says, one alpha particle with 2.9 MeV of kinetic energy rebounds from a different stationary carbon-12 nucleus. Show that the closest separation between the alpha particle and the carbon-12 nucleus is approximately 6 femtometers. Then the nuclear radii was initially estimated using the technique of closest approach of alpha particles. Electron diffraction experiments give more accurate determination of nuclear radii. Suggest why. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've been given the kinetic energy to be 2.9 MeV. Now we then, because we want to work out values in meters later, need to have this in SI units. The first thing we need to do is convert MeV to joules. We know that the conversion from EV to joules is 1.6 times 10 to the minus 19. So therefore the conversion from MeV to joules is going to be 1.6 times 10 to the minus 13, because we've got 10 to the 6 from the M. So at that point we can get our energy to be 4.64 times 10 to the minus 13 joules, and therefore we now want to work out our separation. Now we know that the work done is that's 4.64 times 10 to the minus 13, and we know for the electrical fields that the work done is going to be equal to Q times by potential, so therefore it's going to be equal to Q1 Q2 over 4 pi epsilon 0 r. We can therefore make r the subject, because we know the charge of the alpha particle, it's going to be 2 times by 1.6 times 10 to the minus 19. We know the charge of the carbon nucleus, because there's 6 protons there, so it's 6 times by 1.6 times 10 to the minus 19. So we can work out our values to be 6 times 10 to the minus 15 meters. Now this next question, you've just got to be aware of how you determine the nuclear radii. So the idea is that a small de Broglie wavelength, or a de Broglie wavelength of comparable size to the nuclear radius, will allow you to determine the radius size easily. However, the closest approach method depends on the kinetic energy of the alpha particle, which will affect how close it can get to the nucleus before it will be repelled. So therefore the closest approach, you've just got to know this, provides an upper limit to the size of the nuclear radii, because the alpha particle will not physically touch the outer part of the radius. It'll be repelled by its electrical charge repulsion, so therefore it will be an overestimate. Now the next question says, define the binding energy of a nucleus and then calculate the binding energy of a nucleus of thorium-232. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question you've just got to be aware of the definition of binding energy. So the definition of binding energy is the energy required to separate a nucleus into its individual nucleus. Now the next question, you've got to then use the information given to work out what this binding energy could possibly be. So you know for a fact that you got a proton number of 90 and then a neutron number of 142, because it's 232 minus 90. We can then work out the mass of the protons by multiplying it by the mass of the proton, which is given to you on the equation sheet, and multiplying that value of 142 by the mass of the neutron given to you on the equation sheet. You can then find the difference in mass between those two values and the mass of the thorium nucleus, which is given in the question. You've then got your mass defect, and therefore you can turn this into an energy, and now you've got your mass in kilograms, so therefore you can work out your energy by doing E equals mc squared to get 2.9 times 10 to the minus 10 joules. So this next question says the thorium-232 nuclei absorb neutrons and become uranium-233 nuclei after a series of radioactive decays. Deduce the proton number and the nucleon number of R. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to be aware that when you have absorbing a neutron, well, you're going to increase your neutron number, but not your top number, okay? And you've got to be aware that with the beta decay, you're going to not change the top number, but you're going to increase the value in the bottom by 1. So what you can see here is that if you're going to conserve the numbers for R there on either the middle line or the bottom line, well, therefore the proton number needs to be 91, because from the middle line, 90 equals 91 minus 1, and then again on the middle line we know the value is going to be 233, because 233 equals 233 plus 0. The next question says uranium-233 nuclei undergo neutron-induced fission. One possible fission reaction is shown below. Table 2 shows the binding energy per nucleon for each nuclide. Calculate in joules the energy released in the fission reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you've got to work out the binding energy for each of the values by multiplying the binding energy per nucleon by the number of nucleons for each of the values, which is given by the top number for each one. So you work out the binding energy for each one of those values and you get them in MeV. You then got to find the difference between the neutron and the uranium, okay, which is the starting nuclei, and the exon, the SR, and the three. Remember, there's three of them, three neutrons, because that's the products afterwards. And then at that point, you find that difference, okay, which is expected to be 182.33 MeV. Then you can convert that into joules by using your conversion factor, which is 1.6 times 10 to the minus 13, as explained before, to get your answer to be 2.9 times 10 to the minus 11 joules. The next question says, when a large number of nuclei of uranium-233 undergo fission, the average energy released per fusion will be different to your answer in the previous question. Explain why. Then the critical mass of uranium-233 is 16 kilograms, so that the radius of a sphere of uranium-233 of critical mass is approximately 6 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to be aware that different fissions will produce different types of nuclides, and these different nuclides will have different bind energies per nucleons, which will give a different difference in bind energies, which will give a different energy released. Now in this next question, we've been given our density and we know what the critical mass is, so we know density and mass, so we can work out the volume by doing density is equal to mass over volume. Now therefore we can use the idea that the radius that the object, the nucleus, is a sphere, because it tells us that in the question. So we know that the volume of a sphere is 4 over 3 pi r cubed. So at that point we can work, we've got V from the equation density equals mass over volume. We know 4 over 3 because it's a number, and pi because it's a number, so we can work out what r is going to be, and we get 5.9 times 10 to the minus 2, which is approximately 6 centimeters. The next question says, this ratio of surface area to volume for a 3D dimensional object is sigma, where sigma equals surface area over volume. So determine sigma for the sphere in the previous question, then explain why a cylinder of uranium-233 with a mass of 16 kilograms is unable to sustain a fission chain reaction. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've just got to be aware of how you can link the surface area and the volume for a sphere. So we know that the surface area is 4 pi r squared, and we know that the volume is 4 over 3 pi r squared. So we can cancel out the values of 4, we can cancel out the pi's, we can cancel out 2 of the r's present, so we therefore get that sigma is going to be 3 over r, and then at that point we know what the value of r is from the previous question, so we can work it out there to be about 50. Now the next question is explain why it can't sustain a fission chain reaction. It's the idea that we need, on average, for a sustained chain reaction, 1 neutron on average per fission event to then go on to lead to another fission event taking place. Now the idea is, if you've got a large surface area, most of those neutrons produced in the fission events will leave the actual object without causing another fission event, because it's less likely to hit another nucleus. So at that point the fewer neutrons will induce less fission, so at that point there'll not be enough neutrons produced to lead to a one-to-one fission event each time, so it cannot maintain that fission process. The next question says, define the activity in the context of radioactive decay. Then a dice rolling experiment models radioactive decay. The standard 6-sided dice are used. One dice represents one radioactive nucleus, and at time t equals 0 there are n0 dice. The dice are rolled, and the dice showing 6 dots on the top surface are removed as shown. The number of n of remaining dice is counted. The process of rolling, removing and counting the dice is repeated at intervals of 1 minute. In this experiment, the variation of n with time t can be modeled mathematically with n equals n0 e to the minus lambda t. Explain why lambda is approximately 0.2 minutes to the minus 1. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing is you've just got to know what the definition of activity is, which is the number of nuclei decaying per unit time, per second. It can't be per second, it's per unit time. So it's the number of the nuclei that decay in a particular time. Now, how is this value for lambda going to be 0.2 minutes to the minus 1? Well, we know that on average, when you roll a dice and there's no loading of the dice, that one dice in 6 will actually roll that value of 6 dots. So therefore, the chances getting that is 0.17 is removed each minute for every one dice. So therefore, what you can do do is you can work it through by doing that. You can say that you work it through to be 0.16, so therefore it's going to be roughly 0.2. Now, the next question says, estimate the time t at which n equals n0 over 2. And then say this experiment is done with n0 equals 500. Estimate using the mathematical model for the variation of n with time t, the time t at which n equals 20. Then explain why the actual time taken may be significantly different to your estimate in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you should know that n over 2 is going to be 1 half-life, because that's what the definition of half-life is, the time it takes to drop from n to n over 2. So we can therefore look at our equation sheet and see that half-life is equal to log 2 over lambda. So what we can therefore say is we know that lambda from our previous question is going to be 0.17 or 0.12. So at that point we do log 2 over that value of 0.17. So therefore we can work it out to be 3.8 minutes or 4.2 minutes if you use the actual value that is given precisely, which is 0.17. Then the next one is we sub in our values to n equals n0 e to the minus lambda t. We've then got to rearrange it and we've got to make t the subject. Again, remember, if you want to take an exponential down to be a common term in your equation, you've got to use natural log. So we would say that natural log n over n0 is equal to natural log e to the minus lambda t. So that natural log and e will cancel through. So we know that natural log n over n0 is going to be equal to minus lambda t. So therefore we can work out what t is after we've done that. We know what n is, okay, which we know to be, so we know what n is and we know what n0 is, because you know n is 20 from the question, n0 is 500, so you can work it all through. Remember that we got our decay constant lambda in terms of minutes, or minutes to the minus 1, so if you keep it in that value, we'll get our answer in time in minutes. So you work it all through and we get 19 minutes. Now, why will this be significantly different? Well, if you think about it, from the question we're told, if you look on here, we've only got about 500 dice. So that's only a really small number of dice, and rolling dice is a completely random event. We've assumed that it's going to be equal probability, but we don't particularly know that. So therefore, it's different to decay processes because rolling of dice is also a discrete event, and the rolling and whilst the decay is happening continuously. So therefore, it might be completely different. So that brings us. So the first topic we'll look at is gravitational fields. So the first question says, the lines in figure 4 show the shape of the gravitational field around two stars, G and H. Compare, with reference to figure 4, the masses of G and H. Then the next question says, X and Y are 2 points in the field. Annotate figure 4 to show the field direction at X and the field direction at Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, it's important that you know what a gravitational field shows. So you can see that G has the greater mass. How can you see that G has the greater mass? Well, we know that because the field lines coming from G are closer together, and the density of the field lines tells you about the gravitational field strength, which is linked to the mass of the object. The greater the gravitational field strength, the greater the mass of the particles. Now the next question is asking what would you draw for X and Y. So it's important to note that what you would do is you draw tangential arrows at X and Y that flow towards G and H, because a field line in a gravitational field will always go in the direction of a test mass, and because the gravitational force is always attractive, that means the test masses will always be going towards the particles that are shown, so therefore the field lines will be going towards the objects. The next question says, a spherical asteroid P has a mass of 2 × 10 to the 20 kilograms and the gravitational field strength at its surface is 0.40 newtons per kilogram. So use this to calculate the radius of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is you can look on your equation sheet and you can see that the gravitational field strength is equal to big G m over r squared. So you've realised you've got the mass of the object, you've got the gravitational field strength, and you need to work out the radius r. Now what you should do is rearrange the equation to make r the subject, so r is equal to the square root of big G m over small g, pop in the numbers and you work your answer through to be 1.8 times 10 to the 5 metres. The next question says, sketch on figure 5 the variation of the gravitational field strength G with the distance r. The distance is measured from the centre of P, and then explain what is represented by the area under the graph between r equals big R and r equals 2r in figure 5. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you should understand is as follows, that the gravitational field strength is linked to the distance by the equation G equals big G m over r squared. So because G and m in this instance are constants, we can say G is directly proportional to 1 over r squared. So it's going to follow the inverse square graph. So it should look like so, but what you should also be doing is working out what the values are. So you can see that when the radius is equal to r, well then the value is going to be 0.40. When it's equal to 2r, well again it's G is proportional to 1 over r squared. So therefore it'll go down by a factor of 4 because we've doubled the radius, so there comes 0.2. You can then do the same for 3r to then show that particular relationship, and making sure that you actually work out the individual values. Now again, what is represented by the area under the graph? Well, it's important to know that the area under the graph represents the work done for an object of 1 kilogram or per unit mass to move from r to 2r. So again, it's very important to know what graphs show in AQA A-level physics, and remember you can work it through by saying that the area under a line is going to be the y-axis value times by the x-axis value, so that tells you it's going to be the work done in this instance. And remember, it's for a test mass because that's what definitions come from, and it's going from r to 2r. The next question says, asteroid P approaches the two stars G and H. Figure 6 shows one position of P close to H. Now the gravitational force on P from G is 6.38 times 10 to the 12 newtons. Now the mass of H is 3 times 10 to the 25 kilograms, and the mass of P is 2 times 10 to the 20 kilograms. The distance HP is 1.5 times 10 to the 11 meters. Calculate the magnitude of the acceleration of P. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? Well, what we know straight away is we're asked to work out magnitude, and we've been given something like the gravitational force, so how can we link it all together? So what we can say is we can say F equals G m over r squared to find the force between P and H, because we can tell straight away that there's going to be the gravitational force between P and H, but also P and G. So you can work it through. So you can work it out by saying F equals G m over r squared. Remember, big M is the mass of the larger object, small m is the mass of the smaller object, r is the separation between the two centres of mass. So you can work it out to be 1.8 times 10 to the 13 newtons. Now what we can see is we've got a right angled triangle where we have two sides of the right angled triangle, and we need to work out the resultant. So we can use Pythagoras. And again, it's very important that you can recognize when you've got to use trigonometry in different examples in physics. So we can then say F total square is equal to the square root of the gravitational force between P and H squared plus the gravitational force between P and G squared, and then you work it through to be 1.9 times 10 to the 13. Remember, it's important to note that the gravitational force will be a vector, so you've got to consider what the overall vector is going to be on that particular object. We can then use the equation F equals ma to work out the acceleration. There's always a big alarm bell going off when you've been given a force and asked to work out an acceleration that you're going to have to use Newton's second law. So acceleration is force over mass. We can pop the numbers in, so it's 1.9 times 10 to the 13 over 2 times 10 to the 20, so we get 9.4 times 10 to the minus 8 meters per second squared. The next question says, the global positioning satellite GPS uses satellites to support navigation on Earth. One GPS satellite is in a circular orbit at a height h above the surface of the Earth. The Earth has a mass of big M and a radius of r, so that the angular speed of the satellite is given by omega is equal to the square root of gm over r plus h cubed, and then calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first thing to note is we're trying to show the angular speed, so how can you work that through? So it's very important that you can relate the gravitational force, okay, which is going to be gmm over r squared, is going to be equal to ma. That's important because it's shown that it is the resultant force in this situation, but it's also equal to the centripetal force, so therefore equals mv squared over r. So at this point we can then work through our value of omega. Now again, you can work through the values. Now straight away you actually probably can think that because we need to work out our value in omega, that maybe it's better if we have our centripetal force in terms of omega. So instead of using mv squared over r, we could maybe use mr omega squared and then work our value through. So we can say gmm over r squared is equal to mr omega squared, and then what you can do is cancel through the small m's because they'll be linked together, make omega the subject, so you can say omega equals the square root of gm over r cubed. Now r cubed, it works through to be r plus h cubed because actually the radius that you're going to work out, the small r, is the distance from the center of the object to where the center of mass of the object producing a gravitational field to the center of mass of the object that is in orbit. So in this case it's going to be the radius of the planet, big R, plus the circular orbit height, h. So it works through as so. Now in the next question, you're going to have to use this equation. So we're going to have to use this equation of omega equals the square root of big G m over r plus h cubed by popping in all the numbers from the previous question. Remember, we work in meters in our values to get our speed, our angular speed in radians per second to be 1.45 times 10 to the minus 4. We can then look on our equation sheet and see that the time period is 2 pi over the angular speed. So you're 2 pi over the value to get 4.3 times 10 to the 4 seconds. Always look on the equation sheet to see how we can link the values together. The next question says, figure 3 shows the orbital plane of the satellite inclined at the angle to the equator, and x, y and z are locations on the Earth. X is at the North Pole, y is on a high mountain, and z is on the equator. The satellite is to be launched from one of these locations. State and explain which launch site, X, Y or Z, minimizes the amount of fuel required to send the satellite into orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you can either consider it in terms of speeds or energy. So the answer would be Z, because you've got to think about the idea that at that position the satellite has the largest initial speed or the largest kinetic energy from the Earth's rotation, because you should be understanding that at the equator we've got the highest angular speed. So at that point we can then understand that it'll have the most kinetic energy from the Earth's rotation itself, so it'll need the least amount of energy from the fuel that is given to have enough energy to escape the Earth's gravitational field. The next question says, the satellite has a mass of 1,630 kilograms. Calculate the gravitational potential energy of the satellite when in orbit in the previous question. And then a different satellite is in a higher circular orbit. Explain how the linear speed of this satellite compares with the linear speed of the satellite we worked out previously. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important we understand how we can work out the gravitational potential energy. Now again, because we're looking at orbits, we can't use the equation E equals mg delta H. We've got to use the equation that gravitational potential energy is equal to minus gmm over r. Now we've got big G, it's a constant. We've got the two masses because we've got the satellite mass and we've got the mass of the Earth, so we can pop those into the equation. We then divide it by the separation between the centre of the Earth and the satellite, so we can work it through to be minus 2.44 times 10 to the 10 joules. Now again, remember, gravitational potential energy is always given as a negative value because the gravitational force is attractive, and we set infinity to equal 0 gravitational potential energy. Now the next thing is we can see how the linear speed of the satellite compares with the previous one. Now we've just looked at the idea of how we can work out angular speed, but how can we work out the orbital speed? Well, we can work out the orbital speed by equating the values of the gravitational force equation, F equals G mm over r squared, to equal mv squared over r, and then make v the subject. So with that we can work out our orbital speed to be v equals the square root of gm over r. Again, you always should understand how to work out the escape velocity from equating energies and work out the orbital velocity from equating forces. So therefore v is directly proportional to 1 over the square root of r. So by that logic, you can see, in fact, that the higher orbit will have the smaller linear speed from that justification. Let's have a look at some questions on electrical fields. So the first question says an isolated solid conducting sphere is initially uncharged. Electrons are then transferred to the sphere. State and explain the location of the excess electrons. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you can tell that the electrons are going to be located on the outer surface of the conducting sphere, and that the electrons will be equally spaced on this sphere. Why is that? Because the electrons will mutually repel each other because they're all negatively charged, so they'll want to spread away from each other as much as possible due to that electrostatic repulsion, so they'll be equally spaced out on the surface. The next question says, figure 3 shows how the electrical potential V varies with distance r from the centre of the sphere. The radius of the sphere is 0.10 meters. So the magnitude of the electrical field strength E is related to V by the equation E equals delta V over delta R. So determine, using this relationship, the magnitude of the electrical field strength at a distance 0.30 meters from the centre of the sphere, and state an appropriate SI unit for your answer. Then the sphere acts as a capacitor because it stores charge at an electrical potential. Show that the capacitance of the sphere is approximately 1 times 10 to the minus 11 farads. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, it's important to note that you've got to work out the gradient by saying, well, obviously E is linked to V by E is delta V over delta R, so from the graph that's going to be the gradient. Now it's going to be the value at 0.30 meters, so because it's curving you will have to draw a line as a tangent which only hits the curve at 0.30 meters. You've then got to explicitly show how you work out the gradient of the tangent by literally drawing in your gradient triangle, and it's got to cover at least 50% of the line drawn from your tangent. You then work out the value through and you get an answer of approximately 2 times 10 to the 6. Now what's the units going to be? Well, if you think logically about this, it's going to be V, okay, over M, because we're doing the potential over the distance, so it's going to be 1 unit over the other unit, which is volts per meter. Or you could also remember the units for electrical field strength from the definition. It's the force per unit charge, so it's newtons per coulomb. Now in this next question, what do you do? Well, you can work out what the value of V is. The value of V, it can work out your value of charge by saying V equals Q over 4 pi epsilon 0 R. So you can then look on your graph and work out what the charge would be by saying Q equals V times by 4 pi epsilon 0 R, and then you can work out that value. Now you've also got the electrical field strength at 0.30 meters, so you've got your electrical field strength there. Now because it's a capacitor, we can say that the capacitance is equal to the charge over the potential difference. So therefore we've just worked out the charge in the previous time to be 2 times 10 to the minus 5 divided by your potential difference, which you can then work out to be 1.8 times 10 to the 6. So we get our capacitance of 1.1 times 10 to the minus 11 farads. Or you could also work the other way and say that, well, C equals Q over V. We can work out V by doing V equals Q over 4 pi epsilon 0 R. So therefore C is going to equal 4 pi epsilon 0 R times by V, and work it through to be again 1.1 times 10 to the minus 11 farads. The next question says, electrons leak away from the sphere with time and the amount of energy stored by the sphere decreases. At one instance, the magnitude of the electrical potential of the sphere has fallen to 1 times 10 to the 6 volts. Calculate for this instance the change in the energy stored by the sphere. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this particular question? So, you'll note that E is equal to a half CV squared. Now, how do you know that? Well, that's given to you on the equation sheet. How do you know to use that value? Well, you think you've just worked out C, you've got V in the question, so it allows you to easily work out your value. So you can work out what the energy stored is going to be at 1 times 10 to the 6 volts. So then what we can do is then work out the energy stored when it's fully charged. Again, you can see on the graph when it's going to be fully charged. So at that point, you can work out that value there. You find the difference between the two, so it's 18 minus 5.5 to get 12.5 joules. Let's now have a look at some questions regarding capacitance. So the first question says, a capacitance of capacitance 63 picofarads is made from 2 parallel metal plates separated by an air gap. The capacitor is charged so that it stores a charge of 7.6 times 10 to the minus 10 coulombs. It is then isolated. A sheet of mica of dielectric constant 6 is inserted between the plates so that it completely fills the space between them. The mica does not discharge the capacitor and does not change the separation of the plates. Firstly, explain what is meant by a dielectric constant of 6. Secondly, mica is made up of polar molecules. As the mica is inserted, the capacitance of the capacitor changes. Explain how the polar molecules cause this change in capacitance. So pause the video now, then unpause the video when you want to go through your answer. Right, well, this first question is asking you to fundamentally define what we mean by dielectric constant. So the definition of dielectric constant is it's the permittivity, which is the ability to make an electrical field, of the medium divided by the permittivity of free space. So what we are saying by that is that the permittivity of the medium, the actual dielectric, is 6 times the permittivity of free space. It can find it easy to generate electrical fields by 6 times the magnitude compared to what free space can. The next question is asked us to understand how polar molecules can change the capacitance. So it's important to note that polar molecules align anti-parallel with the electrical field. So that means the positive side of the polar molecules aligns with the negative plate and vice versa. So because they're all lined up, that will produce a very coherent electrical field from the polar molecules. But because they are aligned in the opposite direction, anti-parallel to the actual uniform electrical field, it will produce an electrical field in the opposite direction, so it counters the electrical field between the uniform plates and reduces the field between the plates. So as a result, the potential difference has now been reduced, but the charge remains the same. So because C equals Q over V, well, that tells us that the capacitance has increased, that the capacitor finds it easier to store more charge between the plates. The next question says, a capacitance of capacitance 63 picofarads is then made between the 2 parallel plates separated by the air gap. Now calculate the difference between the initial energy stored by the capacitor and the energy stored when the mica has been fully inserted. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this one? Well, we know in this question that the charges remain the same. So we know Q is the same, but the new capacitance is 6 times out of the previous one because the dielectric constant is now times by 6. So when we look at the equation, for example, you can look at your dielectric constant equation by saying, C equals A over epsilon 0 epsilon r d squared. So what you can say by that is the new capacitance is going to be 6 times the size of the previous ones. So you can work it through by saying if Q remains the same but capacitance goes up by a factor of 6, well, then our energy difference is going to be 3.8 times 10 to the minus 9 joules. The next question says, figure 1 shows the structure of a variable capacitor used for measured angular movement. The capacitor consists of 2 semicircular metal plates. These plates are parallel and are separated by an air gap. To vary the capacitance, one of the plates is rotated through an angle theta using a spindle. The other plate remains fixed. So sketch a graph on figure 2 to show how the capacitance C varies with theta as the spindle is turned through 360 degrees. When theta is 0, the plates completely overlap. So pause the video now, unpause the video when you want to go through your answer. Right, in this question it's important to note that you will get your biggest capacitance when the plates are fully overlapping, because you'll then get the biggest potential difference between the 2 plates. So the positive and negative will form the strongest uniform field when they're completely overlapping. So you can see that when they're completely overlapping, that they're going to have the biggest value of C. Now when they're not in alignment, when they're not overlapping, so to 180 degrees, well, therefore you're going to get a capacitance of 0, and then it bounces back up as it moves to 360. 60. Now it's important to note that it's going to be a linear decrease and a linear increase because you've got a constant rate of rotation, and you can think about how they will overlap, and that will constantly change how much overlaps. The next question says, in one situation the variable capacitor is too large for the available space. The same maximum capacitance is required using plates that have half the diameter of the original capacitor. Explain with numerical detail 2 ways in which this can be achieved. So pause the video now, then unpause the video when you want to go through your answer. Right, how do you answer this particular question? So you've got to think how we can have the same maximum capacitance required when using half the diameter of the original capacitor. So you look at your equation for your parallel plate capacitor of C equals A over 4 over epsilon 0 epsilon R d squared. So you can see that you can either insert a dielectric between the plates, and it's important to note that you would increase it by a factor of 4. So as a result, you can then counteract the fact that you got half the diameter, because if you remember in the equation we don't have diameter but we've got area, so diameter links to area by a factor of a square. So when the diameter is halved, okay, what that's going to tell you is the area is going to go down by a factor of 4, so therefore we've got to put a dielectric of 4 in to counteract that difference. But the other issue you can do is you can change that value of D, so you can reduce the air gap to a quarter of the size, again because it's being divided by that. So as a result, what it'll do is you'll have a quarter of the area and a quarter of the diameter, so the separation, sorry. So as a result, the two will cancel through to get the same value. Now note it says explain with numerical detail, so with that we actually had to say how much the value will be changed. Let's now have a look at some questions regarding thermal physics. So the first question says, figure 1 shows an electrical steam iron. Water from a reservoir drips into the electrically heated metal plate. The water boils and steam escapes through the holes in the metal plate. The electrical power of the heater inside the iron is 2.1 kilowatts. Assume all the energy from the heat is transferred to the metal plate. The metal plate has a mass of 1.2 kilograms and is initially at temperature 20 degrees Celsius, and the heater is switched on. After a time t, the metal plate reaches its working temperature of 125 degrees Celsius. Calculate your value of T. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing you notice is in the question you're given the power. Now you should also remember that with specific heat capacity, that the equation where that incorporates in is that energy is equal to mc delta T. Now we also know that E is equal to PT, so what we can do is we can work out what the energy is, or in this case which says Q, by doing the power, which is 2.1 times 10 to the 3, because we don't work in kilowatts, we work in watts, multiplied by the time in seconds. Now again, if you read the question here, it says that it has been on there, so it's been on for time t, so we can say that it's going to be equal to 2.1 times 10 to the 3 times by t. We can then say, well, that substitutes into Q, and then equals the mass, which is 1.2, times by the change in temperature, which is 125 minus 120, times by the heat capacity. We then rearrange it and use that to work out T, which is 27 seconds. The next question says the metal plate is maintained at its working temperature. Water 20 degrees drips continuously onto the metal plate. Steam at 100 degrees Celsius emerges continuously from the iron. The maker claims that the iron can generate steam at a rate of 60 grams per meter. Determine whether this claim is true. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, what you've got to understand is that the power supplied in time t will raise the temperature of the mass of the water and convert it into steam. So what you should be doing is you should then be using an equation to work out different values. So what we can say is that the energy supplied, which is the power times by time, is equal to mc delta t plus ml, and as a result we can use that to work out what P is, because in the question we've got the heat capacity, we've got the specific latent heat, okay, and then what you can then do is we've got the mass as well, so as a result we can work out what the power is, and then as a result we can link that back into how it can generate steam at 60 grams per minute by working it out as such. So you can work that then through to work out your value. So you can work out your power to be 2.6 6 times 10 to the 3 watts. We can then work out how many grams that would then convert per minute, and then you can see if the value is correct. Now again, it's really important to note in these questions you actually answer the question asked. So you've got to evaluate and say whether the claim is false or whether the claim is true. So the idea is it is probably false because, okay, it's not going to be supported by the values because the calculated quantity you're going to get is going to be not the same as the value that you need. The next question says, in the kinetic theory model, it's assumed that there are many identical particles moving at random. So state two other assumptions made in deriving the equations PV equals a third N mc RMS squared. Then explain why molecules of a gas exert a force on the walls of a container. Refer to Newton's laws of motion in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, you've just got to know the assumptions of the molecular kinetic theory. So they are the volume of the molecules or the volume of the particles is negligible compared to the volume of the container or the volume of the gas. Okay, but remember, you can't just say the volume of the gas, you've got to say the volume of the container which the gas is in. And then you can also say that the collision time is negligible or it's very small compared to the time between the collisions when the particles are in motion. The collisions between all the particles and the containers are elastic, which means that kinetic energy and momentum is conserved in these collisions, and that finally there are no attractive forces between the molecules or the particles when they exist in the gas state. Now you can also got to be able to explain how a gas can exert a force on the walls of a container, which links back into paper 1 and the idea of mechanics. So it's the idea that when a particle collides with the side of a container, there will be a change in velocity, so therefore there'll be a change in momentum. Why is that? Because we're changing direction, and velocity is a change in speed or a change in direction. Or if you want to think about it mathematically, it goes from a positive momentum to a negative momentum, so therefore there's a change in the momentum of the molecules. So what we know from Newton's second law is that Newton's second law is the idea of that the resultant force is linked to the rate of change of momentum. So because there's a rate of change of momentum, there will be a force produced onto the wall. Now again, with Newton's third law, the force on the wall and then the force on the molecule must be equal yet act in opposite directions because they are a third law pair. So you've got the same magnitude of force, the same type of force, but they act in opposite directions on different objects. So as a result, you'll get a force on the particle. The next question says, a sealed flask of volume 0.35 meters cubed contains an ideal gas at a pressure of 220 kilopascals. The mean kinetic energy of the gas molecules is 6.7 times 10 to the minus 27 joules. So calculate the amount of gas in the container. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this particular question? So first question is, how can we link this the different equations together? So we should hopefully know that the kinetic energy of one gas particle, we can look at our equation sheet and we see that it's 3/2 kT. So straight away we've got the mean kinetic energy of one particle. We know what K is, so we can use that to work out the temperature. So we pop that in and we make T the subject and we get T out to be 324 Kelvin. Remember, in this equation the temperature is given in an absolute, so it's in Kelvin. So then what we can do is because the question's asked us to work out the amount of gas, is we've got to work out how many particles are present. So as a result, we can then use one of the equations to say like EK is equal to a half mc RMS squared, to then we can work out what N is going to be, or we use PV equals a third N mc RMS squared to work out our value of N. Or what we could also do is use now our equation of PV equals nRT to work out small n, the number of moles. So we could say number of moles is PV over RT. We've just worked out what T is. We know R, it's the molar gas constant. It's given in the equation sheet. We've got a value for pressure, 220 times 10 to the 3, because we don't work in kilopascals. And we've got a volume of 0.35. So that allows us to work out how many moles that we have. And then we can work out our answer to say the answer is going to be 29 moles. Now the next question says, figure 2 shows a variation of pressure with volume for a fixed mass of an ideal gas at a constant temperature of T. Draw on figure 2 the graph for the same gas at a temperature 2T. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you've got to have an understanding of what the actual graph is showing, so a PV graph. So you would draw a graph with the same concave shape, because it's going to have the same trend, because it's still pressure and it's still going to be volume. It's just a different temperature, but now it's going to pass at points, okay, where it's going to be higher. So you can see here it's passing through the coordinates of 2 and 8, 4 and 4 and 8 and 2, because you can see that with the increased temperature there, well, it's going to increase both the pressure and the volume of the gas. So you've got to think to yourself, how would it affect it? It would just cause both of them to double. So whilst the PV value is going to be constant, then as a result, okay, it's just going to be increased values, because when you've increased your temperature, well, therefore you've got a higher pressure because the particles are moving faster, and also you're going to increase volume because the particles are moving further. So it's the same trend but just higher. Let's now have a look at the magnetic fields topic. So this question says figure 7 shows a transformer. Explain the functions of the core and of the secondary coil in the transformer. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's the core and what's the secondary coil? You've just got to know this. The core is what provides a great flux linkage, or increases the flux linkage from the primary coil to the secondary coil. So it's directing, it is concentrating, it is funneling, it is focusing the linkage from the primary coil towards the secondary coil. Now, what is the point of the secondary coil? That is where we get a change in magnetic flux linkage passing through it, or there's a change in magnetic flux linkage, the field lines going through a conductor. So as a result, because there's a change in flux linkage going through the secondary coil, it tells us that we're producing an EMF or inducing an EMF. That's Faraday's law. So therefore, we can work out what the actual value of the EMF is going to be by looking at the ratio of the number of turns of the secondary and the number of turns of the primary. You can see that's a big deal in the question, because they make a big deal about having a different number of coils on this particular transformer. Now the next question says figure 8 shows the cross section through a transformer core. The thin iron sheets are separated by arterial M. Explain how the efficiency of the transformer is increased by constructing the core in this way. And then figure 9 shows a schematic diagram of a power transmission system. Voltages between 33 kilovolts and 400 kilovolts are used for long distance transmission. Suggest why engineers have chosen 132 kilovolts for this system. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you should understand is when you see an M in this particular transformer, well, M is going to be a insulator. Now, when we cover a material in insulation, that is called lamination. So these laminations or laminates are made from an insulator or high resistivity material. Now, why do we have this? Well, this reduces the impact of eddy currents in the transformer, because they've got such a high resistance, you won't get a high current forming. Now, because if you look at the question, it's 3 marks, we need to think about other features of this which will increase the efficiency of the transformer. Well, you've got to think of the idea that because we're using thin sheets or laminates of iron, we'll get smaller EMFs induced in the core, so we won't get that high enough eddy current. And also we'll note that the thin sheets of iron are used, so the resistance is going to be higher, so as a result, once again, our eddy currents will be lower. Now, the other thing to note is it makes a big deal that we're using iron in the core. Now, the iron is important because the iron can magnetize and demagnetize very easily. It's a soft magnet, so therefore what you're going to have is you're going to have it's not going to have much energy loss due to hysteresis. So that's another reason. Now the next question, why would you use 132 kilovolts for this system? Well, you've got to look at the different values and compare, because if the voltage is lower than 33 kilovolts, then the power transmitted is at a high current. Think about why this is, because V and I are inversely proportional in a transformer. When V goes up, I goes down, and vice versa. Now we know the equation for power loss in a cable is P equals I squared R. So if we have an increased value of I, it will have an increased power loss in the cable. So as a result, we don't want it any lower because we'll have the current is too high. But then you've got to also think, why does it have a really high volts? Why not higher than 132 kilovolts? Well, it's because if the voltage is too high, this will create major difficulties with keeping the circuit insulated and isolated, because there'll be a massive potential difference with the surroundings, so therefore it could cause an electrical discharge. So you can't have that big of a potential difference. Remember, electrical shocks are caused by a large potential difference between the objects. The next question says the industrial consumers use 72 megawatts of power. Transformers 1 and 2 each have an efficiency of 98% and the transmission line has an efficiency of 94%. Calculate the current in a 25 kilovolt line from the power station. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to remember that efficiency is going to be the useful power out divided by the total power in. Now, we can also use that the current is P over V to work out particular values. So what you've got to do is you've got to work out at each point in your national grid system what the power is going to be after you've considered the efficiency of that, and then what you do is at the end you work out the current by doing I equals P over V, from the P that you've just got left and the V that you've got right at the end, because you know it's going to be 25 times 10 to the 3. So the first point is at 132 kilovolts. We know that it's got an efficiency of 98%, so we do 132 kilovolts times by equals 72 over 0.98, so therefore we're going to have 73.5 megawatts at that point. And then you can see that the next section, that's going to have an efficiency of 94%, so we multiply that by 0.94 and we get that's 94%, so therefore the transmission at the start is going to be 78.2 mega EV. And then what you can do is then work it all through, and then you can work out your values, pop them all in, work it out the end by doing I equals P over V to work out our answer to be 32,000 or 3,190. Let's now have a look at the nuclear physics topic. So the first question says fission and fusion are two processes that can result in the transfer of the binding energy from the nuclei. State what is meant by the binding energy of a nucleus, then calculate in MeV the binding energy of a nucleus of iron 5626 Fe. So pause the video now, then unpause the video when you want to go through your answer. So the first question is all about definitions, and you've just got to learn it. That the binding energy is the work done to require to separate the nucleus into its individual nucleons, its individual protons and neutrons. So it's how much energy is needed to separate out your nucleus completely. Now the next question, how to work out the binding energy. So what you've got to do is you look at the values here and you work out the mass defect. Now you work out the mass defect by working out the masses of the individual nucleons, and then we subtract the mass of the nucleus from that, because that's the difference. So we see that there are 26 protons in iron, so we do 26 times by the mass of the proton. That is given to you on the equation sheet. You can see here that 56 minus 26 is 30, so we've got 30 neutrons, so we know that we do 30 times by the mass of the neutrons in kilograms, which is given on the equation sheet. You add them together to get the total mass of the individual nucleons. You then subtract that from the mass of the nucleus, and then as a result you then got your mass in kilograms. You can then convert that into joules by doing our equation E equals mc squared. Now that gives us our value in joules, so E equals the mass deficit times by the speed of light squared. We can then convert that into MeV, because the conversion between joules to MeV is times by 1.6 times 10 to the minus 13 joules. So we get our answer out there to be 490 approximately. Now the next question says figure 10 shows how a graph of average binding energy per nucleon against nucleon number for common nuclides. So the nuclide labeled X in figure 10 undergoes fission. Annotate figure 10 to show one possible pair of nuclides resulting from the fission of X. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So you've got to think that F1 and F2 have to be to the right of the peak, and they're marked on there in the x-axis. Now again, they've got to be in the correct region, so they're symmetrical to about half the nucleon number. So what you've got to understand is that the two values have to approximately add up to equal that value of about 240. Now again, you've got to remember that it won't exactly add up to what the value was for the original nucleus, because you'll lose a couple of nucleons to become free neutrons to then carry on the fission process. So you'll see here they've got to be roughly symmetrical, two smaller values, they add up together to then give a couple of values smaller than the actual nucleus that you started with. The next question says, figure 11 shows a graph of N against Z for stable nuclides. Deduce the likely mode of decay of F1 and F2 and refer to figure 11 in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to do is you look at what the values are for the fission fragments given in your first question. Now you'll notice that in this NZ graph that all the fission fragments will want to move towards the stability belt. Now the issue with both the fragments that you'll produce is they'll have a high ratio of neutrons compared to protons, N to Z. So that tells us that we've got too many neutrons compared to protons. So therefore we want to get down to the stability curve, we want to move closer to the stability belt. So as a result we've got too many neutrons, so we've got to turn a neutron into a proton, so therefore it's going to have to be the beta minus decay, because in that process you're turning a neutron into a proton, so as a result it will move closer towards that stability belt.